Go.
Good afternoon, everyone. Welcome to the seminar of the Astronomy Department of IAG-USP. And many thanks for joining us through our digital channels, or if you are there at the auditorium in person. And today we have the pleasure of having Dr. Rohan Naidu as a speaker. So many thanks, Rohan, for accepting our invitation. Rohan Naidu got his PhD degree from Harvard University in the US, and currently he's a NASA Hubble Fellow and Pappalardo Fellow at MIT Kavli Institute for Astrophysics and Space Research. And Rohan is broadly interested in the first galaxies that formed after the Big Bang, and he studies both galaxies at the highest redshift and ancient systems that lie buried within our own galaxy. And Rohan today is going to talk about the first glimpse of the first galaxies with James Webb's Space Telescope. So I would ask everyone to please turn off microphones and cameras during the presentation, and the questions can be asked after the talk. And if you are following through YouTube, you can also ask questions. You can write it down in the chat, and we can read it later. So Rohan, whenever you are ready, you can start sharing.
Okay, is this visible? Am I audible?
Yeah, both.
Okay, excellent. Thank you so much for having me today. I'm very excited to talk to you all. I'm particularly grateful that you all are making time to come here about galaxies and JWST amidst the World Cup, which I know is a very important thing that's happening. And I was particularly grateful that Brazil is not playing today, so I would have more of your attention. But yeah, without further ado, I'm going to give you, I'm going to share some recent excitement that we are all collectively undergoing as a field, thanks to this new amazing telescope, JWST, and walk you through some results and some ideas about what's going to happen later this year as JWST keeps taking data. So to ground this talk, I'm going to use this figure, which is one of my favorite figures in all of astronomy, just because it contains so much in such few pixels. So starting all the way at the left, you have the Big Bang, and you see in a greenish hue here some representation of the cosmic microwave background. Shortly after the Big Bang, the universe is plunged into darkness. There's no stars, there's no galaxies. All we have is this vast, barren, dark ocean of neutral hydrogen, out of which the first stars and the first galaxies begin to emerge at some unknown epoch that we don't quite know yet. And one remarkable thing that these first stars and galaxies do is they start heating up this very cold sea of neutral hydrogen that they're born within. And this heating up takes the form of these ionized bubbles that start forming around these galaxies. These ionized bubbles begin coalescing. They start to overlap. And this is a period that we call reionization, where the universe goes from a cold, neutral hydrogen place to a hot, ionized place that we currently live in. And then today, we are sitting in a galaxy like this one, and trying to make sense of everything that has come before us and put together this picture of cosmic history. So in today's talk, I am going to touch on two topics broadly. First, I'll discuss some new emerging constraints about these first galaxies, about when they were born, what their properties are, and some surprises that we are already seeing within the few months of JWST operations already. And as a second topic, I'll discuss how these galaxies reionize the universe. What are like the open questions there, and how we are going to go about solving them. One really profound thing about being in this field that I still do not get used to, it's kind of like mind-boggling. Every time I think of it, it makes me quite amazed, is that when we study this cosmic history, we can really directly observe history as it is happening. We're able to see everything everywhere all at once. To use an analogy, it's almost like if I was in your auditorium today and I was looking out of the window and I, was just staring intently at some patch of sky outside the window, some patch of grass, I would be able to see this particular Brazilian team playing soccer. There's Ronaldinho here, there's Ronaldo. They're playing right there. They're just about to win the World Cup. If you look even farther away, you might see this map of your city of São Paulo from the early 1900s, where all these buildings that you might be familiar with today are under construction. And if you look even farther away, you might be able to see some dinosaurs frolicking across South America, right? And that is kind of what we are able to do when we study the very distant universe, when we study these galaxies at very large distances. We can really see history as it is happening simultaneously, and that is something that is quite a mind-boggling privilege that we always remind ourselves of in this particular field of studying galaxy evolution through cosmic time. Another way to look at this is from this very nice cartoon that the national broadcaster in Japan, NHK TV, they decided that everybody should know about what the first galaxies look like and what redshift looked like. And the idea here is that when we're perceiving these very distant galaxies, right? So here's a representation of a very young, one of the first galaxies forming as this baby. And you see that as the light from that galaxy travels to us, this light preserves an image of the galaxy as it was when it formed. But in parallel, of course, it is evolving. This baby is going through, college, midlife, retirement. But we, of course, perceive it as it was when the photons left this galaxy so long ago. And that is kind of how we are able to study this vast span of cosmic history simultaneously. So the light that is coming to us from each of these galaxies from various distances is carrying a photo frame of what these systems look like at various epochs of their life that are frozen in terms of when those photons left them. And so this is how we are able to actually directly observe the very distant, the very first galaxies that formed. In terms of technical capabilities, in terms of how this works, how we are able to separate these very distant, very early galaxies from the ones that are nearer to us, this is kind of how that works. Yeah. So what I'm showing you here is the spectral energy distribution of a very distant galaxy. So here I'm holding this galaxy at a redshift of about 3. So that is about 11 billion years back in time, about 2-3 billion years after the Big Bang. And this is what this galaxy looks like as a function of wavelength in the Hubble Space Telescope's filters. So the Hubble Space Telescope is able to really study objects from the optical. So this is, you should read this in terms of F160W is a filter that collects light at 1.6 micron. F435W is a filter that collects light at 0.4 microns, so in the visual range. So these are optical bands, and you stretch all the way out to about 1.6 micron in the infrared with the Hubble Space Telescope. And you see, what I'm going to do now is I'm going to take the same galaxy, which is at about a redshift of 3, about 11 billion years back, and I'm going to push it farther and farther out, and let's see what happens to what this galaxy looks like. Yeah. So what's happening is as you move this galaxy to larger and larger distances, there's 2 things going on. One, as you move to higher redshifts, because of the expansion of the universe, your light is stretched out all the way into the infrared. So these very distant galaxies, just because of an effect very similar to the Doppler effect, like the classic ambulance moving away and it sounds different. In an effect analogous to that, all the light from these very distant galaxies is shifted predominantly into the infrared. That's one effect. The other effect that really helps us see these very distant galaxies and pick them out as such is that they are completely undetected in these bluer bands. And what is happening here is that these very early galaxies are surrounded by these vast oceans of neutral hydrogen that I was just talking to you about. And what happens in those oceans of hydrogen is that they completely soak up all the blue photons from these galaxies that are capable of ionizing hydrogen, that are capable of exciting emission in hydrogen. And so due to these two effects, due to the expansion of the universe, due to this complete soaking up of blue light by the surrounding hydrogen of these galaxies, what you see is this very characteristic signature where these galaxies are detected only in these very red infrared bands and in no other bands at all. So this is how we go looking for these very distant objects. And as you can see, with the Hubble Space Telescope, we really could push to about redshifts of maybe 11, because that is 11 or 12, because that is where our reddest infrared band lay. Okay, and so the most distant known galaxy today that is spectroscopically confirmed is this object. It is called GNZ11. It was found in 2016 with the Hubble Space Telescope, and you can see here that it's really pushing our facilities right to the very limit of what we could do with Hubble. And this is really where JWST comes in. So JWST comes in, and it was really built to extend the reach of HST beyond this 1.6 micron barrier all the way out into the infrared, so we could really see these first galaxies forming at large distances. And this is what it looks like, yeah? So with JWST, we are now able to go all the way out to about 5 micron with very sensitive imaging that is much deeper than what we had with the Hubble Space Telescope. Just for context, looking at the deepest Hubble fields, JWST is able to match the depths of those fields that took several dozens of hours to construct in a matter of a couple hours. And so this is one such image of one of the first images that JWST took of the very distant universe, where you already see within a few days of operations, we were able to find an extremely distant galaxy that I'm showing you over here, an example of. And you see this galaxy is very, very well detected in all these infrared bands. It's extremely bright. And then it suddenly completely disappears at about 1.2 microns. And so this is a signature that is very, very characteristic of these very distant galaxies. And so this is what the spectral energy distribution looks like, where you have this really bright object that then suddenly disappears. And we were able to find this object already within a few days after the first early release data from JWST came down. And so this is an object that we fit to be at a redshift close to 11, close to the most distant galaxy that we knew with the Hubble Space Telescope over so many decades of operations. We were already able to match that within a few days of JWST turning on. Just to give you a sense of how powerful this instrument is in the kind of era that we are now entering. And not only this galaxy, we found another one. We found 2 of them in these first data sets that were remarkably bright, where like this signature of them disappearing in the bluer bands was so strong that that all our models basically said that they had to lie at these very large distances. We call them glass Z11 and glass Z13, and they lie somewhere between 300 to 400 megayears after the Big Bang, a few hundred megayears. Yeah, this is quite a whirlwind experience. Just to give you a sense of all the excitement of those few weeks of. It is quite an experience to see these images that we made on our computers just kind of like bounce all around the world, really. And it really was because of Captain America. So it turns out Captain America, Chris Evans, is a huge fan of space science in general, and he was also very excited about this very distant galaxy that we found, and decided to tell his few hundred million followers about it. And it really went around the world to the point where even in my small hometown back in India, the local newspaper just carried this small article, and some of my high school science teachers that I hadn't really heard from in so long were sending me news clippings of this. It was just quite the experience to see how much astronomy and so much of what we do really has a way of striking a chord with so many people around the world, and that JWST and its discoveries really means so much to so many people. So after this initial burst of excitement, with these first two very bright, very distant sources, several other teams also found other galaxy candidates that lay at very high redshifts, at these redshifts that we had never really charted before in great detail. So these two sources themselves have now been recovered in over a dozen papers at these very, very large distances, including with some follow-up data that I'll show you in a bit. For the next few slides, what I'll focus on is not the very large number of these high redshift candidates that have been reported, but I'll focus on the very bright ones, because that is where our models are really being challenged. And I'll walk you through why that is such an interesting challenge, and why it is really forcing quite a rethink of early galaxy evolution and what we know about it. And so just to get a context of why this is a surprise, why these objects are really pushing our models, here's a very state-of-the-art sophisticated projection for how many bright galaxies we should find. And so the idea was that if we ran JWST for an entire year, then maybe at the end of the year, in our deepest surveys, we might find a handful of such objects at the end of the whole year, at the end of cycle 1. But here we were, within a few days already, exceeding these projections of how many very bright galaxies should exist. Another way to look at this is if you look at here I'm showing you a plot of how frequent you expect galaxies to be, the number density of galaxies, as a function of their brightness, of how bright an object is. And what I'm showing you here is, in dotted lines, a classic Schechter function. I'll describe what that means in a second. Basically, it is a theoretical prediction that works really well at lower luminosities. It works really well at a whole variety of redshifts, from redshift 4 to 10. But what you see here is that these galaxies lie about a factor of 30 to 40 higher in terms of their number densities that we derive from these early JWST data. Even the earlier galaxy that I was showing you, GNZ11, the one that was found in 2016, was also remarkably bright. And it hinted that these kind of galaxies, that there's something interesting going on where you expect a much larger frequency of these galaxies. You're seeing a much larger frequency of these galaxies than you expect from our best models. The line that's going through here is just kind of like an empirical fit to what we are seeing. But where is that coming from? What is the physics that's driving that is very much an open question. To put this in a larger context of why this is interesting and why this is surprising, is that we've had a lot of success with a very simple model of understanding how galaxies throughout cosmic time form, essentially as a function of their dark matter halos. So what you can do is you take a large n-body simulation of pure dark matter only structure formation, and you pick out any halo in it, and you consider what the accretion rate onto that halo is, the accretion rate of dark matter. And you convert that into some kind of star formation rate by assuming some efficiency, some efficiency that takes your dark matter accretion rate and converts it into a star formation rate. And that gives you your that gives you the buildup of stars in any given like dark matter halo across cosmic time. And so this very simple prescription has worked very well across, redshift 4 to 10 to 11, whatever observations we had. And it predicts this very rapid drop-off at early times in terms of the overall star formation density of the universe. But what we're seeing with these discoveries of these extremely bright galaxies with JWST is that this simple prescription no longer works. The frequency of these very bright objects far exceeds what these simple models that we've been using and that have been very successful are being challenged. And so every time there's a problem or there's a challenge to our paradigm of dark matter and galaxy evolution, of course there are solutions. And so there's been a whole flurry of activity trying to explain how you're able to form such extremely luminous galaxies at such early times. So this is a problem that has been called the quote-unquote too big to be problem, which is that these galaxies appear to be much more luminous, much more massive than what all our state-of-the-art models predict. I'll walk you through a few classes of solutions from this very highly incomplete list, because so many of these new solutions are coming out. Like, every few days there's a whole bunch of them. There's a bunch of them just last week, for example. But roughly, the classes of these solutions are: one is to tweak cosmology. Basically, say that our cosmological model is not complete. We know it's not complete. There's tensions at every scale. There's so many open questions. But what you can do is, if you introduce some kind of early dark energy, you can produce a universe that is older by around redshift 10. So these galaxies get much more time to grow. And because the assembly of these dark matter halos at very early times is quite rapid, you are able to match this constraint. Another class of solutions has to do with the baryons, where you can appeal to a much increased star formation efficiency in certain halos at these very early times. Maybe these halos are extremely dense. Maybe they're able to cool gas much better than the kind of halos that we're used to at lower redshifts. This again is appealing to tweaking with not cosmology, but more the properties of dark matter. And then finally, another class of solutions, which my personal opinion is that maybe the answer is really in this list, is that there's something up with the baryons, right? Like every time there's any problem with cold dark matter, often it turns out that the problem really is not with dark matter, but with the baryons. And so there's a whole class of things that would very nicely explain why these galaxies are so bright. One has to do with maybe the initial mass function is very different at these very early epochs, where the fraction of very luminous, very high mass stars is much larger than what we are used to seeing in the local universe at relatively lower redshifts. Maybe POP3 stars are much brighter than our models predict. Maybe some of these early galaxies are able to form luminous primordial AGN that are shining very brightly, but briefly, and we are catching them as they're forming. And then maybe there's something up with dust physics. Maybe these early galaxies just do not have enough time to build up the dust that dims their counterparts at lower redshifts. And so this excess of bright galaxies might just be the fact that there really is no dust occluding our view of these very early objects, because if you imagine things like AGB stars, which are key channels of dust production, you just do not have enough time for your stars to evolve into the AGB phase for them to start shedding dust, for example. And so that is another possible solution. So it's a very exciting time in terms of, there's some set of new observations that are more than an order of magnitude off our best models, and we are going to try and find ways to reconcile that. Another set of early surprises has been about the morphology. So, for example, this particular object, Glass Z11, has this very disky extended profile that my teammates, Erica Nelson and Ren Cease, analyzed and found where this object seems to be consistent with already having a disk in place within a few hundred megayears after the Big Bang. And this is really interesting. I know there's many of you at the department who are very interested in the Milky Way. And what we see in the Milky Way as well is this new picture that we are forming thanks to Gaia and thanks to large spectroscopic surveys of when exactly did the Milky Way acquire a rotational component. And so what I'm showing you here is the history of our galaxy, of our own galaxy, the Milky Way. So we live in the low alpha disk today. The sun is a star in the thin disk. Prior to that, we had this thick disk. And before that, we had this very chaotic proto-galaxy where there really wasn't any rotational component. But then at some point, around about redshift 4 to 6, we start having a net angular momentum that is prograde, that is in the direction that the sun orbits the galaxy today. And what's very interesting is that the total stellar mass of the Milky Way at this epoch is very similar to this total stellar mass that we derived for these very early galaxies. So perhaps we are learning something about some kind of characteristic mass scale when galaxies are able to acquire some kind of angular momentum and a rotational component. At this point, we are still being cautious and calling some of these very bright, very robust galaxies candidates because there's still some systematic uncertainties that I'll walk you through. So there's chiefly two classes. One is that we're using these new instruments for the first time. For example, we're using this amazingly powerful imager, the NIRCam instrument on JWST. And there have been a lot of updates in terms of the calibration of the instrument, in terms of its 0 points, in terms of its flats, in terms of various calibrations. And so there has been some uncertainty about, are these galaxies actually real, or are they an outcome of these systematic uncertainties? But that's no longer as much of an issue. So all the calibrations are now known for the 0 points, for example, to a less than 5% level. And so that's looking pretty solid. So this is not as much of an issue anymore. The other interesting issue is that there might be entirely new classes of galaxies that are able to mimic this characteristic signature of galaxies dropping out, where you're detecting some galaxy very brightly at a variety of wavelengths, and then it suddenly disappears. So this kind of signature could perhaps be mimicked by some new class of galaxies that JWST is showing us for the first time. For example, here in this paper that I wrote, where I call this galaxy Schrodinger's galaxy, because it could be, it appeared to be at redshift 17, but it could also be at a lower redshift of 5, assuming it is this new kind of galaxy, which is an extremely dusty but very low mass system, whose light appears in this kind of dropout fashion. And hence kind of fools us to think that it is very far away, but perhaps it's actually much closer. And so this is why we really need to get spectroscopy of these systems, and there's been large efforts underway to do exactly that. So there's two facilities that are able to study these very distant galaxies and gather spectra for them. So one of them is close to where you are, which is ALMA. So ALMA in Chile is able to perform far infrared spectroscopy of these very distant galaxies. It is sensitive enough to be able to capture far infrared lines like O3 that is redshifted all the way into the IR at 88 micron. And what we're finding for both these systems is that they do not show any detections whatsoever in these far IR wavelengths. So that's both good news and bad news. It's good news because a whole variety of lower redshift interlopers, like these objects, should show up extremely brightly at these ALMA wavelengths. The idea is that if you're so dusty and you're completely extinguishing all your light, it should be reprocessed and re-radiated in the infrared. And so these galaxies, these kind of very dusty starbursts, should be extremely bright in the infrared, but we don't see anything at all. So that is the good news. The bad news is that we are unable to confirm redshifts for these objects because we do not see anything at all. And the idea here is that you are not seeing these O3 emission lines or dust continuum because these objects are basically very metal poor. So the non-detections basically place an upper limit of about 10 to 20% solar in terms of the metallicity of these galaxies. So what next? So we have ALMA, and we've gotten these results on these objects. With JWST itself, we will be able to very easily measure spectra for these galaxies. So I'm showing you an example of how this will work with JWST. With only about less than 5 hours of JWST spectroscopy, what we'll be able to see is this characteristic signature I was discussing of the flux completely disappearing of this Lyman break, if it is indeed at these very high redshifts, if these galaxies are at these very high redshifts. Versus if they are at lower redshifts, then you see this much more gradual kind of sloping decay in the flux. And so we'll easily be able to distinguish between these two scenarios. And so for some of these very bright early galaxies that are challenging our models, there's a handful of them. So one of them is going to be observed in exactly 2 weeks from now with JWST in exactly this mode. So we will get this data for the Schrodinger's galaxy in a couple of weeks and be able to test whether it is indeed at redshift 5 or redshift 17. I see I'm running short on time. I want to talk to you about reionization as well, but I'll just give you like a taste of what is at stake with cosmic reionization. The key question about how these galaxies reionize the universe really comes down to which galaxies reionize the universe. So is it like a large number of very faint galaxies, or is it a very small number of very bright galaxies? So these are galaxies that I call, quote unquote, oligarchs. And so for the longest time, the prevailing picture in the field has been that it really is like a very large number of numerous faint galaxies, like the Milky Way's ultra-faint dwarfs, basically, that really drive cosmic reionization. But what I and my collaborators have argued is that the latest constraints on reionization really make it out to be a very short, a very rapid process that happens between redshift 6 and 8 in a matter of a few hundred megayears. And this favors reionization by bright galaxies because these galaxies appear only at these later times in terms of their overall number densities. Of course, till now I've been talking to you about how we are seeing these very bright galaxies at very early times, but here I'm talking about like galaxies in the stellar mass range of about 10 power 8 to 10 power 10. And so this really has implications for pretty much every astrophysical question that you care about, because the topology of reionization really sets how galaxy evolution goes across all of cosmic time, because that is how your gas is heated, your gas behaves, and then really sets the tone for star formation. And so how are we going to distinguish between these scenarios? So we have this upcoming JWST program that's going to be observed next week, where we are pioneering this new kind of bubble study, where what we do is we really focus on this one single bubble that we know in the epoch of reionization at about redshift 7. It's a very special bubble because the Lyman alpha spectra that comes out of this bubble really constrains the total size of the bubble. And so what usually happens with Lyman alpha at these very large redshifts is because it is so sensitive to neutral hydrogen, it is completely extinguished. But what we see for this particular galaxy is that we see the whole Lyman alpha profile that is extinguished only at very large distances, which is to say that this galaxy is sitting in a large bubble. And depending on where exactly the flux cuts off, we can really estimate the total size of the bubble. And if you know the size, you know what the total ionizing output is, very analogous to a Strömgren sphere, where the size is directly constraining what the total ionizing photons within that bubble should be. And so what we're going to do is we're going to perform a complete spectroscopic survey of this whole bubble and pick out all the bright galaxies that are within it. And we're going to count the ionizing photons from them and ask if this is going to be enough to really power this whole bubble or not. And so this is a very controlled kind of experiment that we are trying out with this galaxy that we'll know the results of in the next few weeks, which will directly help constrain like what really are these protagonists of reionization. But yeah, on that note, I'll leave you with a summary slide, and I'm very happy to take questions and discuss. Thank you so much for your attention.
Great, thank you so much for this very, very clear talk and very, very exciting, very fresh data that you have. So let's start with the questions. Let's see. So, Guilherme, please, you can go ahead.
Hey, Rohan, thank you so much for the talk. It was quite clear. Even I myself don't know anything about high redshift, so it was quite clear. So thank you for that. I was wondering, like, among the hypotheses that you showed to explain this high fraction of very luminous galaxies at very high redshift, the thing I was wondering is, I am also a fan of the solving the problems with baryons, because I also agree that every single problem on the cold dark matter, on like cosmology that we see, they are always solved with baryons. But on the tweaking cosmology side of things, it's interesting to me, it's also appealing to me that introducing early dark energy is also a solution that people have proposed to solve the H0 tension. So do you know some paper, anyone that has tried to solve both problems at the same time? Because maybe that will be like an approach to try and see what we get out of this.
Yeah, no, that's a really, really great question that you raised. I don't know of any paper that has explicitly tried to like fit both of those constraints simultaneously, but indeed it goes in the right direction. I think the really key thing that we need to do, that kind of like the community is waiting for right now, is like really solid spectroscopic confirmation of like some of these galaxies before like people really like kind of launch into doing much more detailed, I think, theoretical work. Because my read is that there's been this great initial flurry of excitement, but then I think folks are like now a bit confused because we went through that whole like calibration saga, and then there's all these questions about, oh, could it be some new class of like lower redshift galaxies and stuff. So I think we really need to like just get spectra for these and really nail them down, and then I think exactly the kind of study that you suggested, I think a lot of people would be motivated to really put time into doing that in detail.
I see. So we are kind of in this point that people are waiting for the spectroscopic confirmation.
I know. That's my read. Maybe people are. Yeah, that's my read on the theory community in terms of how they're kind of like going around.
I see. Thank you. I will let Professor Elizabeth ask you.
Hi, Rohan. Very, very interesting. Thanks for the very nice review talk. And I have a question regarding this brightness excess, because actually, if you have this excess of bright galaxies in the early universe, this would change completely the extragalactic background light in distribution. Isn't that so?
By extragalactic background light, you mean things like the ionizing background, or do you mean
at this energy range? You know, low energy photon field that provides this extragalactic background light that is so important for very high energy stuff. What I mean, for instance, 1 month ago there was a surprise, some excitement in the high energy astrophysics community, because a GRB, a gamma ray burst, was observed at a large redshift with a luminosity 10 times bigger than it could be at TeVs. TeV, tera electron volt, so very high energy emission. And this was the first emission, the first observation of TeVs in GRB ever done, and with the counterpart of neutrinos. So, and why is that? Why was that so important? Because if essentially according to the background absorption provided by interactions of gamma rays traveling of such big distances with the background photon field, low energy photon field, the EBL, the extragalactic background light, because of this absorption, we would not be able to observe this brightness, right? But it was. So, and then there was this question. So the cosmological models might be wrong. But your findings go in the other way around, that the EBL should be even larger. I mean, this background light can be even larger. So the absorption should be bigger, and we should see, a smaller brightness in gamma rays rather than bigger brightness. So and this is very important, because this may point to the production of the only other way to solve this puzzle is to invoke the existence of axions. So this so it's very interesting, because so I'd like to go into more detail in these papers and in these findings of you guys, because this may change completely the EBL. So the EBL may be larger, and if they are even larger rather than being smaller, then this is a clue for the existence of axions, and then you have a dark matter candidate here. So it's very interesting.
Thank you so much for the suggestions. I hadn't really put all that together. But yeah, the one thing I'd say is that indeed, like, these things appear like to be, and they are like pretty large excesses at these ends. But if you look at the total integrals of star formation rate density across all galaxies at some epoch, across all like brightnesses, right? Like in an integral sense, the super bright things still, like, even if you like amp them up by a factor of 10 and stuff, they contribute more than we expected, for sure. But they're still like a fairly like smaller bucket of the total, like, of all the star formation happening in the universe.
Right. So what you are saying is that this contribution would not affect too much the EBL. In
an integrated sense, yeah. Like if you like integrate across all the galaxies that we know are at the much, much fainter ends, right? Like this plot keeps going all the way. We know at least minus 15.
But essentially, this contribution comes from the reionization, from the first population. So that's why I of course, I have to take a look, and we should evaluate how this might affect the EBL. That'd
be very interesting. I'm excited to see what that calculation looks.
Okay, so I can write to you, and then we may exchange some papers in order to see if this is to understand how this could affect the EBL. I would be very interested in understanding better these effects, right? Okay.
Yep, look forward to it. Thank you.
So I take a contact.
Okay, thank you, Beth. Leandro, please go ahead with your question.
Yeah. Hi, Rohan. So I hope you can hear me.
Yeah, I can.
So yeah, my question is about these morphological classifications of galaxies in high redshifts, and specifically I'm wondering about like the presence of massive clumps in high redshift galaxies. Do you have some updates on observations from JWST on this?
Yeah, no, there's been a lot of amazing work, especially at like lower redshifts, because the resolution is just so much better, and you see all the way into the infrared, and like you really are able to tease apart things like the effects of age and metallicity and color gradients on like what it's doing to morphology. And indeed, like we are finding galaxies are very clumpy and so on, where there's a lot of like merging activity that we see for the first time, right? Like things that are falling in, where like you see the clumps within like these early like knots of star formation and ionizing photon escape and such. So indeed, like it's a very complex and messy picture. But what we're seeing here is, again, like integrating across all those star-forming regions, right? Like we're seeing like this large blob of like UV, basically. So for at least this galaxy, we are not sensitive to that kind of like substructure. But at lower redshifts, indeed, we are seeing a lot of that. And I think one major thing for us to do is to figure out really how to like fully incorporate the richness of that data into our very simplistic kind of like Sursich indices that we fit to all these things, right? So that's indeed like a very exciting field that indeed Ren and Erica are leading some very interesting papers in.
Thanks, Rohan.
Guilherme?
So I do have another question. Rohan, what are the stellar masses of these galaxies that you're showing, like the Galaxies Z11 and Z13?
Yeah, that's something I didn't highlight too much here, but we infer them to be between more than 1 billion solar masses in stellar mass. So between 10 power 9 to 10 power 10 is what we derive for them. So basically, as massive as the LMC, essentially.
Yeah,
but
I was just going to say that.
But at a redshift of within a few hundred megayears, versus the LMC has gotten a chance to live for.
Yeah, I was asking that exactly because isn't it like funny that these galaxies are isn't it funny that these galaxies have like LMC stellar masses and they have these disks shapes, and the LMC also has kind of a disk. So
yeah, that's kind of like the connection I was trying to draw. Like yeah, even for like the basically historical Milky Way of like, perhaps there's something there. But what I'll say though, right, about the stellar masses is it's majorly uncertain, because what you are seeing in light in the UV, right, like the light you're seeing is coming from less than a few percent of the total stars in the galaxy, right, the total stellar mass, and you're doing this big conversion between UV light to total stellar mass, which is notoriously uncertain, because you have to assume some kind of initial mass function. And one of the solutions to this quote unquote too big to be problem is that the initial mass function that we use, right? For example, the numbers that I just quoted to you are using Chabrier IMF. So you could like completely rewrite like an IMF and say that you don't form any low mass stars, not any, but like very few low mass stars at all. And there's some support for this from simulation as well. Then your masses can come down by quite a bit. They can come down to as low as few times 10 power 8, and that is no longer as much of a strong tension with CDM or any of these other models, because it basically is one of the baryon solutions that I was outlining, where basically what we're saying is that these galaxies are bright, but they're not big.
Sure, I see. Also, isn't it possible like to test with simulations, like if we need, like when do disks kind of settle?
I think as you know, you're the Milky Way guru. That's very much a currently open and debated question right now, right? About how do disks form? When does the as you're seeing with like, we have a bunch of papers from our group. There was a paper from Vasily and all in Cambridge about the emergence of the Milky Way's disk. And one of the cool things they show in both these papers is that our current set of simulations just do not match them at all, right? Like these disks are forming much earlier than in most of the simulations, in the vast majority of the simulations. So it's, I think, very much an open question on the simulation side about how we do this.
Yeah, maybe this question regarding like the connection between the formation of disks or the establishment of disks and the stellar mass and the time scales for the formation becomes even more interesting given the JWST data that you're showing.
Yeah,
but, yeah.
And completely independently, there's been some very interesting work from Brant Robertson and their group as well, where they went across all of and Chris Consolise's group as well, where they went across all these early data and ran some interesting algorithms to try and classify morphologically whether galaxies are in disks or not. And they do find hints of like the disky fraction being much larger
of disks, right,
than people
I
predict.
saw this paper as well.
One of them was evocatively titled "Panic at the Discs."
Yeah, I even retweeted this paper.
That's right.
I see. Yeah, I think this is all. Thank you, Rohan.
Okay, so I have a couple of questions concerning how these new results that you obtain, how do you have to change your original observation plan concerning the reionization part? Like now that you know that there are some too big to be galaxies, do you change your observational plan concerning the reionization?
Not particularly, because we just have this bubble, right? And we're going to go see what's in it. And if we find that there's bright galaxies in it, then that's the answer, or not. So it really is kind of like a blind survey of this whole bubble volume, where we're going to pick up spectra for every object that is in the field of view. And so it really is what's in there. We're going to go and try and see. And if indeed there's things there, then we pick them up. But in general, you can't really like. There are exceptions where if you are like looking at like some mask, if you're doing like say slit spectroscopy of some field and you find some very exciting object and you want to like open a new shutter basically because that's how the NearSpec shutter works. I think there is some flexibility there where you can like put in like a change and be like, hey guys, we just found this really exciting object. We would like to open a shutter on it. You're already looking at that part of the sky. Just click a button, right? So I think you can make that kind of change, but not a kind of change where you're just like, oh, we just want to look at some totally different part of the sky.
Yeah, I see. I understand.
Yeah.
So you mentioned that the observation will start next week, in a couple of weeks.
Yeah, so you get like this window basically,
Yeah.
within which it could be scheduled, and this program is being executed in 2 windows. It's a pretty long program, order 20-ish hours. And so the first window starts December 3rd, the last time I checked. So.
Okay, so a lot of excitement on this, but I guess also a lot of pressure, I guess.
It's a privilege, you know? The pressure is a privilege.
Yeah, of course. And I am wondering, when do you think you would have the first like hints on it?
Depends on how fast we are.
I see.
Depends on how much time we want to spend with our families for Christmas, how much of a life we have. But yeah, no, hopefully early next year. Yeah.
That's pretty soon, actually.
Yeah.
How many of you work on the hands-on, let's say, on the data?
It changes from project to project.
Yeah.
On all the results that I showed you earlier about the very distant galaxies, it was basically a fairly large team effort, but it was led by me and Pascal Usch at the University of Geneva. But we had a lot of help on various aspects. You see, like, for example, on the morphologies, Erica Nelson and Ren Cease led that particular effort. So yeah, like, it varies from project to project. That set of projects was possible at such short timescales because we had such a large set of people who were helping us with various things. For this particular project, we have a fairly small team. This is a project I'm working with Jorrit Mate on, who's a Zwicky fellow at ETH Zurich right now. And yeah, we'll again have help from friends, but this one's a fairly small team. It's, I think, order 7 people.
Okay. Yeah, I see. Okay, thank you very much for your answer. Let's see if there is more questions or comments. Okay, so I think I am going to thank you, Rohan, again. Thank you very much for your excellent talk here. And do you want to say something?
No, just thanks so much for having me, and I really appreciate the opportunity to talk to all of you.
Okay,
and share some of the
Thank you.
Thank you very much.
Thank you,
Thanks,
Rohan.
Sylvia.
We really hope to see you in person someday here at Sao Paulo.
I'd love to.
Sure.
I'd love to.
It would be really wonderful. Yeah.
Thank you.
Thanks for having me.
It was a pleasure. Thank you.
Bye-bye. Thanks.
Bye.
Valeu, Maria Vitória.